First of all, thank you to the organizers for the invitation. Today, I'm going to talk about running couplings in higher derivative theories, and particularly in quadratic gravity. This talk is based mainly on two recent works in collaboration with Roberto Percacci, John Donadieu, and Gabriel Menezes. So let's start. So first of all, why study higher derivative theories? As you know very well, Einstein general relativity as a quantum field theory is not renormalizable. But if we add to the action operators which are quadratic in curvature, like Riemann squared, Ricci squared, Riemann squared, fourth derivative kinetic term is added the metric, and this makes the theory power counting renormalizable. However, it has also some drawbacks. In fact, higher derivative kinetic term can introduce some those modes with breakdown of unitarity of the theory at tree level, well known as Ostrogasti instability. From the point of view of renormalization group of theory, there has been many attempts historically to find the renormalization group equation of theory. The first attempt was done by Jules and Tonin, and they found out that the theory is perturbatively asymptotically free in presence only of a scalar tachyon mode. However, they forgot to consider also an initial output ghost, and in fact, a few years later, came another result by Fredkin and Seisin, which stated that the theory is asymptotically free also without the scalar tachyon. But also in this result, there was a numerical error. And finally, in 1985, Avramid and Balvisky found out which is considered the right result for the beta function of the theory. And again, quadratic gravity comes out to be asymptotically free only in presence of a scalar tachyon. From the point of view of the function normalization group, at least at one loop, the beta function are quite similar to to those obtained perturbation theory. So we have a fixed point with lambda MC equal to 0, which corresponds to the asymptotically free fixed point. You can see that also from critical exponents, and many interacting fixed points, which here we have two examples, but there are many others. However, it's not completely clear whether they are physical, they could be a product of an artifact of due to truncation of the action. However, our main question at the beginning of this work was to understand whether those RG equation actually produce the momentum dependence of scattering amplitudes of the theory. In order to understand that, we have to start from the basic definition of running coupling in high energy physics. Let's consider a quantum field theory with coupling G and masses M. At one loop, in perturbation theory, the scattering, a generic scattering amplitude is given by a structure like this, with the one loop correction which contains a logarithm of momenta over the mass scale of the theory. Of course, this logarithm can become arbitrarily big in the high energy limit when P is much bigger than M, and this could provoke a breakdown of perturbativity. In order to avoid this, possible solution consists in reabsorbing the logarithm in the definition of the coupling at a given energy scale P bar. At energy P near to P bar, the logarithm is again small or under control, and perturbativity is restored when G of P bar is small. However, in this way, we are just moving the problem from one point to the other. So we're just moving around this big, large logarithm. And in order to have a real improvement of the situation, one has to consider an infinitesimal transformation of this coupling G with different value of P bar and near one to the other. that permits to define the beta function as the derivative respect to logarithmic derivative respect to the bar of G. And then one can reintegrate integrate this beta function and obtain the RG improved expression of G. That is the so-called running coupling in the scattering amplitude sense. That we will call it. We call this definition of running coupling as the and of beta function as a physical beta function. The concept of running or of running coupling and normalization group is usually strictly related to the concept of renormalization and regularization. Every type of regularization and normalization introduced in the theory physical energy scale, and typical renormalized amplitude again has a shape like this. We have now this logarithm where we have in the argument mu, where that represent the unphysical energy scale introduced by regularization, and above it we have this f, that is a generic function of mass dimension 2 of masses and momenta of the particular scattering process that we are considering. In the end, one expects the physical scattering amplitude to be independent from the physical parameter mu, and that suggests to request the independence of the amplitude A from mu that permits to define another set of beta functions which are given by the Callan-Simanzik equation, and we will call them the mu beta function. In this case, the dependence on mu of the coupling is strictly related to the poles, to the divergences of the loop computation. One can observe that in Nast's theories, there is the only dimensionless quantities that can appear in the logarithm are of the type p square over mu square. And that means that the physical beta function that is induced by logarithm of p is equal to the mu beta function that is induced by logarithms of mu in the massless case. However, this relation is not always true in the case when there are mass scale in the theory. If we start considering the ordinary two derivative theory, in this case, this is the general generic one loop Feynman diagram. It is with its integral. In the low energy, the smaller low energy part of the integral, up to particular collinear and soft configurations of external momenta, which are treated in other ways, there are no. The integral is not divergent. So because there is only 1 over q square in the denominator. On the other hand, we can have divergences from the ultraviolet, the high energy part of the integral. However, in the UV regions, both masses and massless theory are almost equal up to subleading correction. So the divergences are the same, and we can say that the mu beta function for massive theories are equal to the mu beta function of massless theory. And when the reference scale, momentum scale we are considering is above the mass scales of the theory, they are equal to the so-called physical beta function. On the other hand, things are slightly different when we consider higher derivative theories. In fact, in this case, we have this quadratic propagator. That means that also in the low energy part of the integral, the loop integral, we can obtain this expression like this, where we have 1 over q to the 4th, which is logarithmically divergent if integrated t to 0 in q. So we have both divergences from the infrared part and from the ultraviolet part in massless theory. In a massive theory, masses act as infrared regulator. So the infrared 1 over epsilon pole induced by divergences turns into a logarithm of p over m, not related to poles, and then logarithm of the physical mass scale mu. So in this case, the mu beta function of a massive theory is different from the mu beta function of a massless theory, and then is also different from the what we have defined as the physical beta function, even in the high energy regime. So there are two examples in order to clarify what's going on. First, we have a couple integral here with a generic vertex interaction vertex A. We see that in the massless case, this integral is exactly 0 in dimensional regularization. However, if we could introduce a mass scale into theory, we have a 1 over epsilon pole and a logarithm, but this logarithm does not contain any dependence on the external momenta of the process. External momenta cannot enter in the integral interpole diagram. So we have a divergence, mu running, but not a p running or a physical running. Another typical case that we will see even later on in the discussion is the tuple diagram. In this case, in the massless case, we have a divergence coming from the infrared part of the integral is given by a square p to the 4th 1 over epsilon and a logarithm. So we have a mu running and a physical running. But if we introduce a mass, there is no more divergence because the integral is regulated by this mass in the infrared. And so we have only this log of m over p that induces p running without 1 over epsilon pole and then without mu running. In the first moment, we consider a toy model of a shifting metric scalar model with a set to symmetry with a higher derivative kinetic term and a 4-point derivative interaction. Such a derivative interaction can be generated by a spontaneous breaking of U1 symmetry in a derivative linear sigma model, or could be also generated by interaction with gravity in an asymptotic safety scenario. Generalization to higher derivative sigma model has been studied by John Donoghue and Gabriel Menendez. So the one loop correction to the 1 point to the point five, the one loop correction to the 2-point function of the theory are given by this tuple diagram, as observed before. There cannot be dependence on the momenta in the logarithms generated by a tuple diagram. So one can set at any scale the normalization to 1. We have a mu running because it's log and per a function the pair field normalization must depend on mu in order to have the mu independent renormalized wave function. However, there is no dependence on the particle momentum, so there is no physical running. If we move to the one loop correction to the 4-point function, in this case, we have a derivative interaction. That means that there are no, in this particular case, there are no infrared divergences as expected in this bubble diagram here. And we have just threshold behavior, mass threshold behavior as in usual two derivative theories. So we'll see that the situation is different in quadratic gravity. So in at low energy, the one loop correction to the 4-point function is given by this expression. We have just a logarithm of mu over m. So at any scale, momentum scale, below the mass of the part of the closed mode, one can normalize the coupling G once for all, and doesn't need to introduce a random coupling. So we have a new running without a physical run. However, at high energies, if we fix the value of the coupling at the scale m, we obtain this type of amplitude with a logarithm of s over m squared, t over m squared, and u over m squared. St and u are among the standard variables, and this logarithm can become arbitrarily big, arbitrarily large in the high energy limit. So we have to find G in order to preserve perturbativity. So in the high energy limit, the equivalence between the two definition of beta function is recovered. Let's move now to quadratic gravity. This is the direction of quadratic gravity, the cosmological constant, an Einstein integer multiplied by the square of the black mass, by the tensor square, the Riemann scalar square, and the Euler density, which is given by the expression, and in 4 dimensions is the topological term. The spectrum of the theory is given by a spin 2 graviton, massless, a spin 2 ghost with mass proportional to lambda, and a scalar mode with mass proportional to minus psi.
Yeah, may I ask a question?
Yeah.
So in the previous model, so what is the upshot? The beta functions in mu are the same as well, running with mu is the same as running with p, or still tadpoles? Yeah, because I missed what was the conclusion eventually, because you mentioned that tadpoles are
it's different for the two cases. In the case of the field normalization, they are different.
Yes.
While in the case of the coupling G, they are the same in the high energy regime.
Yeah, no, but here, okay, so then let me ask this way. So basically, to remove large logs, we have to take the normalization scale to be equal to momentum. That's what we are doing in the second case. But then the same normalization scale, shouldn't we take it the same to be in the tadpole as well? And then, you know, then there will be like a physical running coming from tadpole.
Yeah, but I don't need to once if I experimentally fix the field normalization at a given scale.
Right, but which scale? So scale where equal to momentum, right?
Yeah.
That's what you are fixing it. So so then I'm taking mu to be equal to p. Well, mu squared to be equal to p square in all the diagrams, right? Because it's the same scale for all the diagrams.
Yes, but the fact is that I don't need to set another time the normalized quantity. That's the difference between the two cases.
No, it's not another time. It's really like I'm taking, you know, I'm performing measurements at certain scale, right? At certain, you know, like physical scale of momentum. Then we see that to remove large logs in certain, you know, in certain vertices, we take the normalization scale to be equal to momentum. Good.
No,
but then I take the same normalization scale in all diagrams, right? Because that's the normalization scale. And that's how tadpoles contribute to running eventually.
Yeah, okay. Okay, yeah, but yes, you're right. But if I have to, but if I would have just the tadpole, I wouldn't need to change the normalization scheme. That's what I wanted to say.
No, I think with this I agree, but kind of my point is that you know, like because I have to take a normalization scale to be equal to momentum, tadpoles will contribute, and actually they do in models. For example, like two-dimensional sigma model, where all the running comes from tadpole. I mean, all the diagrams there are like this one, and they do contribute into physical running, what we believe to be physical running at least. Okay, yeah, let's go on. Yeah.
Yeah, maybe it's a good idea to let Diego continue and we can pick up this discussion after the talk.
Okay, so how to compute the beta function of the beta function of quadratic gravity? What the most used method is background field method. In this case, one separates the metric G in a background part G bar, that is solution of the classical equation of motion plus a quantum fluctuation H. So the action comes out to be the background classical action plus the second variation with respect to the quantum fluctuation of the action of the gravity of the gravity action plus gauge fixing term and ghost action for the Faraday of ghost. So we define H, the action of the action with respect to the quantum fluctuation H. And in the end, one can write the one loop effective action in this way. Thanks to renormalizability, the quantum correction at one loop can be written in terms of a C square term, an R square term, and an older density term up to correction of order mass Planck, let's say, square in the high energy limit. And from this coefficient alpha, beta, and gamma, one can compute the beta function of the couplings of the theory. So now both y and delta ghost can be set can be taken as two derivative operator with the right with a particular gauge choice. So the only higher derivative operator is H, and we will focus on it. In particular, there is a particular gauge where one can reduce H to this form, where there is a minimal particle operator, particle differential operator. The usual way one is H operator distributor consists in using heat kernel that permits to do manifestly covariant computation in perturbation theory. And these are the usual result from heat kernel 1 over epsilon divergences in dimensional regularization. However, we immediately see that this term U and part of this RV term come from tadpole diagrams that we state do not contribute to the physical running. So the Planck mass, that's because we have the Planck mass that acts as an infrared regulator. However, even if we set Planck mass to 0, and we consider the theory without Einstein-Hilbert and cosmological constant, the heat kernel itself includes a physical regulator, and the local internal expansion is unsensible to infrared logarithm of m over p square. So what we did is to return to the first technique used by Jules Ventonin in order to compute the beta function of quadratic gravity. So we expanded again the background, the background metric around the sub background, and we take in this way here, where now H bar is a perturbation of the background. In this way, the Fourier space is well defined, and we can use Feynman diagrams, which if we compute all the integrals, not just the UV part, we can obtain also infrared logarithms. In general, order H bar square is enough to subtract the curvature square terms in the one loop effective action. And so after this expansion, H has this form where delta here represent the flat space-time propagator, plus some correction, some operator D, C, V, N, and U, at least linear in H bar. The trace of the logarithm of h can be expanded in this way here. So this term a1 times 1 over delta is a helpful. So we are not interested in computing the physical running, and all the terms with more than 2 8 contribution will be cubic in h bar, so we don't care of them, and so we limit ourselves to these bubble diagrams with only linear term in h bar in A, because they are the only relevant term in order to have a physical running of R square terms. So if one set mass Planck to 0, the delta operator is just a box square, and this is the resulting bubble integral. And here I written down all the new infrared contribution, the contribution coming from the infrared part of integral, which were neglected before. Notice that apparently they are non-local because they have p to the 4th in the numerator, but you will see that they also contain some local parts which are crucial. The complete calculation with mass Planck not 0 is quite complicated from the computational point of view, because of the different of the complicated tensorial structure of the propagator in this case, because the mass of the tensor of the traces part is different from the mass of the trace part and so on. So we are currently working in order to compute do the computation also with mass Planck and Einstein-Hilbert term. However, we expect that the high energy result is the same. In order to do a check, we use this simplified version with a propagator delta given by both square plus m square box. And what we obtained is that the log of p square is the same result of just a box square, where as anticipated, if we take mass Planck to 0, the log mu gives the same dependence as the log of p, while in this case we have the log p that gives the same result of the box square new results, while the log mu gives the beta function of the if kernel minus tuple contribution. So why actually we have some local contribution from this term? In fact, if we consider all the linear part in h bar in the various interaction vertices, what we obtain are all a contribution of this type, which are p to the 8th power in the numerator and p to the 4th in the denominator. Of course, in general, there could be various non-trivial contraction between these momenta. But thanks to Bianchi identity and integration by part that one can accomplish in the effective action, one can find out a relation like this that permits to write a generic derivative of Riemann tensor in terms of curvature box square curvature terms plus all operator of higher order in curvatures, which would be non-local and subleading in our expansion of small h bar and high moment. This relation are automatically respected by the linearized curvature and by h bar and its derivatives. So in the end, we end up with terms which are all of the type of real structure p square h bar, which corresponds plus non-local term cubic in h bar, so we neglect them at the moment. And all the h bar square terms can be rearranged covariantly in c square and r square terms up to topological and boundary arbitrariness. So these are the results. on the left, we can see all the beta function from its kernel computation. We have the asymptotic safety fixed point correspond to lambda and c equal to 0. We see that lambda always, in this case, always runs to 0 in the UV, while c goes to 0 only with two particular fixed point values for this quantity omega, which is equal to 3 times lambda over psi, and they are both negative. Negative omega corresponds to positive psi, and as we observed before from the spectrum of the theory, positive psi correspond to a tachyonic mode, scalar mode, because the mass proportional to minus psi. So we have asymptotic freedom only present at scalar tachyonic mode. On the right, we have our new results, our new set of beta functions. And we have again the asymptotic free fixed point, lambda going to 0 and c goes to 0, but now we have a fixed point value for omega 1 that is positive and is represented by this green line. So in this white quadrant here, that corresponds to the tachyon-less sector of the theory, this is the unique asymptotically free trajectory. In fact, below this green line, we end up with c equal to infinity, so in a strongly coupled regime in the scalar sector. While above this green line, we finish in the zero tachyon sector of the theory. And we reach this red trajectory. It is also asymptotically free, but with spin zero tachyon. We have applied this kind of computation also to conformal gravity. Of course, topological terms do not contribute to scattering amplitude, so the physical scattering amplitude, as we have introduced in this context, is not defined for the raw coupling, for the coupling from the term, for the topological term, and so it can be computed in this way. From the point of view of the running of lambda, there is no qualitative difference. There are no qualitative differences. There is just a different numerical value here, but the sign is the same. So just a numerical factor. Okay. So in conclusion, renormalization and running are not equivalent concepts in general. In two derivative theories, the variances are strictly related to the running of atoms. However, that's not true in general in higher derivative theories, but it's still true only in the particular case of massless theories with dimensional regularization. The Higgs kernel misses, at least in its local expansion, misses the infrared running effects. And if we take into account also infrared contribution, relative gravity has a unique asymptotically free trajectory without dampers along all its trajectory. Let's go to future perspective. Beta function, one thing that we are doing right now is computing beta function of so-called non-local partner of R and cosmological constant, like this operator here. Yes, we are trying to do it. However, probably this method is not compatible with lambda differences from zero sign. So we have expanded around the flat background, and flat background is not a classical solution in presence of a cosmological constant. Another point is that it would be interesting to reproduce the same result with the non-local kernel expansion. However, at the moment there is no a non-local expansion for the kernel for a high derivative operator or equivalently for non-minimal two derivative operators. Finally, there is some point also. Also, the concept of asymptotic freedom is not completely clear, at least to me. In the case of quadratic gravity, since we have a derivative interaction, and that means that yes, we can have a logarithmically decreasing coupling, but we have amplitudes which depends polynomially on momenta, and obviously a polynomial dependence dominates over the logarithm decreasing. So in order to understand whether there is really real asymptotic freedom in the sense of all cross section going to zero, one has first of all to understand which are the true degrees of freedom of the theory, at least in the high energy limit. It is not completely trivial because the high energy regime is quite tricky in this theory. Then finally we have written a new beta function for conformal gravity, and yeah, that implies also a modification of the conformal anomaly of the theory, and that's another point. Finally, the presence of a unique asymptotically free trajectory, if we are able to continue this trajectory to inflationary energy scale. At the moment, we are not capable of doing that because we are not being able yet to introduce in a complete way the Einstein-Hilbert term in this computation. But potentially one could induce some constraint on the scalar to tensor ratio in CMB, and maybe some experimental proof for quadratic gravity as a asymptotically free completion of quantum gravity. So thank you.
Thank you very much, Diego, for the nice talk.